Yeah.
Yes, sir.
I think last class we discussed up to this. Still, we are going to discuss about different load and different stresses in different components. So, I mean, this information will be very useful when we are going to discuss the further problem in the design the components with respect to different loads or different stresses. Okay. So now we continue from here. Yeah. Yeah, just to recap, first couple of minutes what we discussed in the last class. I mean, first one is tensile load. The bar is subjected to tensile load. The second one is bar is subjected to compressive load. Okay. The third one is the bar is now the two thin bar thick mean the two bar is connected with the help of the rivet. When the load is applied, when the load is I mean crossed beyond this, I mean exit beyond this limit, then that rivet is getting failure due to shearing effect. Okay. Now see here that the third one here, I mean this the plate, the thin plate is subjected into shearing force while the punch is operating on the punching is operating on the operating on the thin sheet. I mean, especially we are using a lot of washers in our engineering, especially mechanical engineering applications. We are connecting two components with the help of the bolt and nut. We are using a lot of washers. The washers we are preparing, we are making from the thin sheet. The thin sheets we are for that operation we are using the punching operation. While preparing the washer is cutting with the help of the punch due to effect of the shearing force, the shearing effect at the side of the side of the washer. Okay. I mean, this is with shearing effect, the washer is cutting from the thin sheet. Okay. Now, come to the next. This also you might have been discussed or studied in this your earlier semester. I mean, here when the bar is subjected to shearing load, shearing force, then I mean this bar, this diagonal M and P is subjected to. I mean now when the shearing force subjected on the top of the bar is deformed, like M is moved to M dash, N is moved to N dash, right? Now the diagonal of the bar M and P is subjected to compressive, but the diagonal of the bar L and N going to be a new position L and dash subjected to tensile force. Okay, I mean based on this concept, if you go for the trigonometric concept, I mean some mathematical concept, apply the mathematical concept, we able to find out the stress strain relations here. All right, I mean with respect to compressive stress, with respect to tensile stress, finally be able to derive this derive the I mean sorry, elastic constant relationship EGK elasticity I mean relationship, E, G, and K relationship. From this, I mean shearing force, we able to derive that. Okay. Now, what are these elastic constant? Just I write the formula for recap. Okay. Then we move to next. I mean, what is this? I mean, E is equal. Please tell me. E is equal to 2G into 1 plus mu. E is equal to, just recap, 2G into 1 plus mu. What is this EGK mu? I mean, EGK mu relation. Someone tell that. EGK mu relations. Okay,
Sorry,
EK.
E is
Yeah, tell me, bro.
E is equal to 3k into 1 minus 2 mu.
Yeah, that is EK relation. E is equal to 3K into 1 minus 2 mu. I mean, EGK relation. Now, all the elastic modeling. I mean, E is Young's modulus, G is shear modulus, K is a bulk modulus. Yeah, please someone tell that. E is equal to You might have studied, no? Nine kg divided by 3k plus g. I mean, k is nothing but bulk modulus. What is bulk modulus? Bulk modulus. What is bulk modulus?
So volumetric stress by volumetric strain.
Volumetric stress. Okay. Okay. Anyway, but exactly incremental pressure divided by change in volume. I mean, change in volume to by original volume. That's nothing but incremental pressure divided by volumetric strain. Okay. Whatever you are saying, correct. But how can you consider volumetric stress? Yeah, anyway, I will give you a small explanation. Because theory, if you might have studied a theory of elasticity subject, I hope that you are very well known about this stress strain relationship. But we just touch that information, then we go for the further discussion. Okay. Now, a bulk modulus is nothing but minus bulk modulus is nothing but a change in internal change in pressure or incremental pressure divided by volumetric strain dV divided by V. I mean, what is the compressibility? Compressibility is inverse of bulk modulus. I mean, dV by V divided by dP. Okay. Now, furthermore information we would like to discuss about this. I mean, see here. I mean, the right hand side, the figure. I mean, this is the bar subjected to own weight. What is the deflection? Anybody? I mean, self weight. The bar subjected to self weight. That is also under static load. Whatever we are discussing, most of the things are under static load. Then what is this equation? What is the formula? Due to self weight, what is the deflection? Due to self weight, delta L is equal to rho G L square divided by 3E, right? 3 or 2E? Rho G L square divided by 2E or 3? Someone please. Rho G L square divided by, I think 2E, correct, 2E. Sorry, 2E. Okay. Now, next thing, I mean, see here, this bolt and nut arrangement. I mean, this is the tube, the steel tube and bolt and nut arrangement. What are the forces? What are the forces are acting here? What are the stresses are acting in this arrangement? Because we have lot of bolts and nuts we are using in our mechanical system to fabricate the components, right? I mean, what are the stresses are involving in this arrangement? What are the
So tensile and compressive.
Tensile and compressive. Thank you. And before going to one more thing, I mean, when the bar is due to rotation, this is now static condition. This is static load condition. When the bar is rotates, when the bar is rotates, what is the deflection? This is now the bar is rotate. Okay. What is the deflection? Deflection when the bar is rotation. This is now under the dynamic condition. What is the, I mean, delta L is equal to 4PL. You might have been studied, but if you didn't study, please at least understand the formula. D1, sorry, D1, no, rho WL squared, sorry. I did small mistake. Rho omega squared, because rotation of the shaft in terms of omega, this is the length of the shaft divided by 12E. These are the dynamic condition. For simply for your understanding, I put it here. Anyway, we are going to discuss in the later. Now the elongation of the tapered bar. The bar is now tapered bar. This bar is now tapered bar subjected into axial load. What is the elongation? Delta L is equal to delta L. Del L is equal to 12 4 P L divided by pi E d1 d2 pi E d1 d2. Okay, now I come to this. Now we continue this. I mean, this arrangement, the tube is subjected to compressive. The rod, the rod in that sense, the rod is nothing but our bolt. The bolt is subjected to tensile load. When we are tightening the nut, when you are applying the torque on the nut, the bolt is subjected to bolt is subjected to tensile, and the tube is subjected to compressive, and the washers are subjected to compressive load. Okay, now one, I mean, there are okay, now we move to this next. Okay, now whatever we discussed, now we'll going to apply this concept for the applications. Now, I mean, I might have been told this before anyway. Now that this is a stress in machine elements. What are the stress in machine elements? There are different stress. I mean, tensile, compression, bending, torsion, and von Mises theory, von Mises stresses. I mean, these are the different types of stresses we already discussed. The von Mises stresses and maximum shear stress, maximum strain energy theory, we are going to discuss in the later. Okay, these are the types of stresses involved in the body. But this thing, sorry, this thing I might have been told earlier, but I missed out. Okay, now when the when the component subjected to tensile load, what will happen? This is simple component, right? Now this is the particles. Now when the component subject to tensile load, this particle, I mean, subjected to the load is acting this direction. What for because of the resisting force created uh, in the particle. So each particle resisting force created, each particle, right? Hence this is the this is called, we are saying the stress. When you are applying the load here, this is external load, this is called a stress. This is the particle is try to resist our external load. Similarly, compressive stress. Now we come to the tensile stress. I mean, tensile stress is nothing but P by A. Compressive is nothing but it's a compressed area P by A. Okay, now see here, the rivet is single rivet is used in this arrangement. In these the two plates are connected with the help of the joined with the help of the single rivet. Okay. Now that steering force, I mean, we know that when the two forces are acting in the plate, then the rivet going to be failure because of the steering force, shear stress, right? The shear stress, what is the shear stress? P by A, then P by pi by 4 into d square. This is the diameter of the rivet head, diameter of the rivet, not rivet head. This is a rivet head. Here, diameter of the rivet. Okay. Now, now I am using two rivets. I mean, tau is equal to P by A. Here, number of rivets is 2, then multiplied by 2 into pi by 4 d square, right? Then, suppose if I would like to use, I mean, more number of rivets will be better, or less number of rivets will be better for try to avoid the failure. You might have been seen components, some components, right? You might have been seen some component, might have been used many rivets, right? For example, even if you see the car wheel, the drum, the tire and drum connected by sometimes 6 bolt, sometimes 4 bolt, right? Then why, I mean, more number of rivets will be preferred for will it be preferred for avoiding the failure, or less number of rivets will be preferred for avoiding the failure? Which one is better, more rivets or less rivets?
More rewards, sir.
Yeah, thank you. More rivet will be better. See here, I mean, here we are using single revert, the shear stress is more. But when you are using more reverts, the shear stress acting in the revert is less. Hence, better we have to use more reverts or more join, more bolts and nuts. It can be avoided that shearing force acting in between the component, in between the plate, in between the thin sheet or component, the same shearing stress will be acting on the revert. Hence, we can avoid the shearing force or shearing stress in the revert as well as in between the component. Hence, we can avoid the failure. So that's what people are going for, more reverts. But one more thing is there. I mean, when you are even more and more rivet will be going there, then it will be the strength of the component will be getting reduced. Okay, that's what we have to appropriate is, and I mean, study we have to do before going for the number of rivets. But in general, number of rivets will be better to avoid the failure. Now I come to, I mean, furthermore, these are the stress strain relations. Okay, in the stress strain relations, okay, and 1 minute, and you might have studied volumetric strain, and maybe few students may not recollect the information. Just I go through the brief explanations, then we come to this formula. Okay. Yeah. See here, volumetric strain. Volumetric strain for different case of sections, we are going to discuss. There are three cases. One is rectangular section, another one is circular section, another is sphere. Okay, I mean, very brief explanation I'm going to give you here. I mean, volumetric strain for volumetric strain, EV. I mean, EV, right? Suppose EV or epsilon V, volumetric strain for rectangular section. I mean, here we know, right? V is equal to L into B into T. Then now I'm going to differentiate with respect to here each. I mean, I'm going to differentiate in this. dV is equal to now BT dl plus LT dB plus LB dt. Okay. Now divided by volume, both side divided by volume, right? Here LBT, then finally we are going to get dV by V is equal to dl by L minus here dB by T dB by B minus, because here I am considering minus sign because this region, when you are applying the tensile load, this is the region along the breadth side, along the thickness side going to be reduced. Hence, I am putting minus sign. Okay, in actual case, in practical conditions, we are putting, based on practical condition, I am putting minus sign here. Okay, now see here. I mean, you can rewrite this equation. Now, this is nothing but I can consider this is the strain with respect to, I mean, axial directions. Okay, now 1, right, minus, this is now nothing but mean E times, okay, I write it here. Now this is E times strain minus, I mean, I'm introducing Poisson ratio 1 by m. This is nothing but minus Z. This is 1 by m. I'm delta T, dt by T, I'm writing in terms of Poisson ratio. I'm using that E. Okay. Now, see, you take it common. Now, this is E into 1 minus 2 2 by m. This is nothing but E into 1 minus 2 mu. Okay. Now, this is epsilon V. This EI, how can I write? The E, I can write it in terms of S sigma by E, Young's modulus. Now, sigma E by Young's modulus, sigma by E into 1 minus 2 mu. Okay. Now, this is with respect to x direction. This is with respect to along thickness, breadth direction. With respect to breadth, the stress is acting. This is the stress is acting along the thickness side. Okay. Now, in this case, indirectly, I am taking that sigma x is equal to sigma y is equal to sigma z is equal to sigma. But now I am going to introduce sigma x not equal to sigma y not equal to sigma z. Then how can I write the equation? I mean, during that time, I can write the equation now sigma with respect to x. Okay. Now sigma x, E is a common for material property, all the direction homogeneous. Sigma x minus, I mean, sigma mu into sigma y minus mu into sigma z. Okay. Now this is the for three-dimensional volumetric strain. Now similarly, I take for a circular cross section, volumetric strain for circular cross section. Apply the same concept. This is second case. This is first. Now volumetric strain pi by 4 d squared into L. Finally, you are going to get dV is equal to similarly E into 1 minus 2 mu. Similarly, volumetric strain for sphere. This is for cylinder. This is for sphere. Okay. This is for sphere. V is equal, this is sphere. Okay. This is sphere. Now, V is equal to pi by 16 into d cube. Okay. Now, then dV by V is equal to, finally you are going to get 3 into delta d by d. Okay. So now I come to for next slide. Now, I mean, see here, if the material is subjected to stress only one direction, the corresponding strain is nothing but, I mean, what kind of stress this is? Uniaxial load. I mean, uniaxial stress, you may say that uniaxial stress, based on that the strain is sigma x by E. Suppose the stress is acting in y direction, they induced in y direction. Suppose the stress is acting in y direction also. Then, I mean, we can take, then now this here, epsilon y by epsilon x, epsilon z by epsilon x. I mean, this is nothing but our Poisson ratio. Okay, nothing but Poisson ratio. Now, the epsilon x is axial strain, epsilon y and epsilon z are the lateral strains. You are very well know about this. Now, I would like to write whatever we discussed earlier, we derived the equation. I would like to write in terms of two-dimensional way. I mean, two-dimensional way in that sense, I mean, I can consider, for example, earlier case, sigma x minus mu into sigma y minus mu into sigma z. Sigma z I am considering 0 in two-dimensional case. Any one direction avoiding this stress component, then I am considering that. Okay. Now epsilon y is equal to 1 by E into sigma. I mean here the sigma. I mean the stress is 0 here. Sorry, sigma z is going to be 0. It's nothing but a plane stress case. You can consider plane stress case. Plane stress case, the same equation. Now I write it here. You can understand. Now, yeah, okay. First, we think about. I mean, please avoid this now. First, we think about this equation 1.24. That's what we can easily understand. Now, I mean, for 3D case, first we discuss, then we go to top. For the 3D case, when the bar is subjected to sigma x, sigma y, and sigma z, 3 stresses. I mean, that's what we discussed. I mean, here the strain with respect to x direction, but while considering the all stress component, then that's what we discussed just now. 1 by E equals sigma x minus mu into sigma y minus mu into sigma z. Right? Now epsilon y, with respect to epsilon y, we are considering the all stress component for finding the strain. Okay, now with respect to z direction strain, but while considering the all stress component, okay, now this is the total net strain, epsilon x plus epsilon y plus epsilon z. The summation is going to be given total total or net strain. Now this equation bring back to here. Now I am considering the plane stress case. Just to put sigma as at 0, then it will be a plane stress case. I mean, these equations widely we are going to use in the further calculations. Even when you are going to study in advanced center material, this is very important relationship. I mean, now we have written in the equation epsilon. I mean, it's a strain in terms of stress and Poisson ratio. The same this equation, if you solve this equation, you are going to get stress in terms of strain. Stress in terms of strain. Okay. Now I come to the whatever we discussed for when the single component subjected to tensile stress, compressive stress, like that. Now we are going to the component. For example, the rod in different application means how these used, how the component used, how the component is positioned or located for our application. Based on that also we can define now. I mean, this also might have been studied. We go through the briefly and recollect the information now. Okay, just a recap. Now cantilever beam. I mean, in the cantilever beam, this is what kind of behavior? Linear behavior or line? This is a line. So I write it, so don't waste of time. Now see here, I mean, cantilever beam, the SFX, shear force at with respect to SFX, we already know is equal to minus W. This is a straight line. Okay, this is a straight line. There's a D diagram, because this is very important when we are going to discuss the further topics, the components of design. This is also very important when you are going to discuss the next semester DTE, design of transmission elements. I mean, even the last semester I was teaching this subject. I'm going to teach the same subject DT in the upcoming semester. Maybe. Okay. Now this is what is the bending moment with respect to x here up to this. Here bending moment mx is equal to minus wx. Now this is linear. Now the bending moment is linear behavior. Now I come to this when the beam cantilever beam subjected to uniformly distributed load. I mean, what is the bending moment? Shear force. Shear force at x. At x, shear force is now the minus wx. This is the first order polynomial equation. Then this variation is linear. But I come to this. I mean, bending moment at x. W minus w x squared divided by 6l. Now this is the second order polynomial, hence this is the parabolic curve. Because based on that, the stress behavior going to be there. Now I come to but where we are applying this concept. I mean, as I told you that now this is the fixed shaft. In this shaft, the flywheel, with the help of the bearings, the flywheel is connected. Okay, help of the bearing, the pulley is connected. Now the pulley may rotate. With the help of the motor. Then for some applications, then we would like to understand. I mean, we are going to use this same concept for defining the size of the shaft or dimensions of the shaft. Okay, that's what. Now we are doing a recap about this topic. Now I come to the I mean, when the shearing force and bending moments are in the different loading conditions. Now the right and left hand side, this is, I mean, when the cantilever beam is subjected to uniformly varying load, then what is this? Load, bending moment, and shear force behavior. I mean, shear force behavior now in this case, now cantilever uniform varying load, right? Oh, sorry guys, one small mistake I have done here. This is W into x by 2. W into one small mistake, sorry. Minus W into x into x by 2. This is what cantilever beam subjected to into uniformly distributed load. Now cantilever beam subjected to varying load. Just here SFX shear force with respect to this x. Now W minus WX squared by 2L. This is parabolic. Now this is now this is now cubic curve. When this bending moment in this case cubic curve, mx is equal to minus W x cubed divided by 6L. Okay, now the right hand side is simply supported beam. Simply supported beam, the shaft whatever we discussed in the earlier slide. Briefly we discussed the simply supported beam concept. Now the shaft is connected with the help of supported with the help of the bearings B1 and B2. Now this is the pulley going to be connected to the motor, right? This is pulley during power transmission. Now what type of deflection now? This is belongs to, it looks like a simply supported concept, simply supported beam concept. Now that concept we are going to use for defining the maximum, we have to find out the maximum deflection where it is, maximum bending in shear force, and maximum bending moment where it is. Based on that we are going to define the dimensions of the shaft, this shaft. Okay, now what is this? Simply supported beam. SFX is equal to nothing but W WL by 2 minus WX. Now this is simply supported, sorry, W by 2. This is W by 2. Minus W by 2, because this is straight line. Now I come to this bending moment. Come to this bending moment. Bending moment is nothing but Wx by 2. Here Wx by 2. Mx is equal to minus Wx by 2. Wx by 2. Now this is a linear. Okay. Now I erase this. Because I have to write the equation in the same slide. Same slide. I put moving slide here. Hence, now this is the, I think, okay. Now this is the simply supported beam uniformly distributed load. In the uniformly distributed load, yes, SFX is nothing but WL by 2 minus WX by 2. This is X is varying linearly, first order polynomial. Okay, this is linear. Now here bending moment is nothing, bending moment is here W bending moment WLX by 2 minus WX squared by 2. This is a second order polynomial. It's like parabolic curve. Okay, now I come to next. This is the uniformly, this is uniformly varying load. Uniformly varying load. In this uniformly varying load, right? This is the parabolic now. The shear force is varying parabolic behavior, but in the bending moment is varying in cubic behavior. Okay. Now I come to, this is the shear force, deflection, and bending moments at a different case of loading condition, at a different case of bending, supported beam. Okay. Now we move to this simple conclusion here. This shear force diagram will consist a rectangle when the bending moment is loaded in the point load in cantilever beam. But the shear force diagram will be consist inclined lines when the portion of the UDL load, when UDL load, uniformly distributed load in the cantilever beam. The shear force diagram will consist of parabolic lines. Whatever we discussed, I kept it here. Parabolic lines when the portion of the beam in triangular load or trapezium load. Okay, in the simple cantilever beam. Okay, this is same thing what we discussed earlier. This now, this is the shear force diagram will be consist of cubic when the portion of the load in parabolic in the simple cantilever beam. Now this is the bending moment. Now this is now bending moment diagram. The bending moment diagram will consist of inclined lines when the beam is subjected to free point load in the cantilever beam. We discussed already. Okay. Similarly, when the bending moment will be consist of cubic or third degree polynomial if the load is distribution is triangle load in the triangle load, this right triangle load, right? Yeah, in this simple cantilever beam. Okay, so just go through these points, very useful when you are going to have a minor one. Okay. Now bending stress, come to bending stress, and now this is the section how the bending stress is acting. You might have been studied here. I mean, what is this axis? In this axis, bending moment. Why bending moment is? Means bending stress is 0. Anyone? Why bending stress is 0? I would like to ask some 1 or 2 questions.
Sir, it is neutral axis, and on that line, what do you say? The beam doesn't undergo either compression or tension, sir.
Exactly. Because the beam deformation is 0 in this region. I mean, the beam we assumed as per the studies, Bernoulli's theory, right? I mean, we don't know what is the exact reason, in-depth reason, but people gone through proper studies and analysis and research, then they came to know that with the theoretical analytical study and experimental study, they came to know that the beam where the neutral axis lying in that axis, the beam structure doesn't deformation, hence we are considering the no stress. That is 0. But when the beam when the load is acting the beam, the top portion may be compressive, the bottom portion may be a tensile. But here in this case, with respect to neutral axis, the stress is either bottom portion is higher stress or lower. Bottom portion is higher stress or and top portion higher stress. We can define with respect to the neutral axis, position of the neutral axis. Suppose, see here in this diagram, see here sigma c is greater than sigma t, because suppose the neutral axis, because see here this is the web, this is a flange one for bottom flange, then top flange, but both flange in same size, then now this is the top flange, this is the bottom flange. If both flange is same size, then that sigma c equal to sigma t. Sigma c is equal to sigma t. But with respect to that's what I'm saying, that with respect to neutral axis. The neutral axis with respect to the design geometry of our component. That's what I'm saying. Now if this both top flange and bottom flange both are same size, identical dimension, then your neutral axis lying at the middle of the beam, middle of your component. Hence both sigma c and sigma t during that time it will be same. Okay. Now this is, you might have been studied here. I would like to just tell here. What is this? Right? Just we go brief explanation. Top flange. This is web. This is centronist web. Then bottom flange, BF. Now, what is this area? 8,000 mm square. This area is now 8,000 mm square. Web. This I am here considering this web area. Okay. That the bottom portion area is, bottom flange area is 4,000 mm square. Okay. Now, what is the centroidal axis? Centroidal. How can I find out the centroidal axis? Suppose this is centroidal axis with respect to this flange, 20 mm. Okay. This is a bottom centroidal axis, 20 mm. What about this central axis? 40 plus. This is 100, then 200. In this is what is the middle? 200. 200 divided by 2, 100. 100 plus 40, 140. What is this centroidal axis? This centroidal axis 260. Where is this centroidal axis? These are the informations will be required when we are going to find out the our bending stress, right? I mean, bending stress, right? M by I is equal to sigma B by Y. Now, this is I is here a complex structure. There are complex. This is not uniform structure, right? Because here one web is there, here one flange, here web is there. There are different dimensions. Hence, we have to find out our moment of inertia with respect to this axis. I mean, here IA moment of inertia with respect to x is nothing but IXX is equal. Just recap. Okay, I mean I for top flange plus I for bottom flange plus I for web. Then this is our IXX. I mean, why do we need? This is now nothing but our Y bar. This is nothing but our Y bar, neutral axis, where it is acting neutral axis, right? Then we have to find it out. What is Y bar? Y bar is nothing but Y bar is equal to epsilon A Y divided by epsilon A area, total area. Here this is the epsilon A. You have to find out, right? This is our this is our Y for each component Y. Now this is multiply this epsilon ay, then multiply this and this multiply, and this multiply. I take another color. These two multiply, this two multiply, this two multiply. Put it here. Then find out epsilon ay, epsilon ay. Finally you are going to find out Y bar. Now bending stress. Now bending stress, how can you find it out? Bending stress is, use these relations. Sigma is equal to sigma C is equal to M by I into YC. Now Y you know, right? You can find out easily. Now this is the another example. Sorry, 1 minute, I deleted. Yeah, in this bar, see now bottom, where this is very close to bottom portion of the web, bottom portion of the web, right? Hence here less stress, but here more stress. Okay, more stress. Top portion subjected to more stress as compared to bottom portion. Depends on the neutral axis, neutral position, it can be varied. Suppose one more web is here, both are in identical shape. Suppose one more web is here, then obviously that sigma C and sigma T both are same. Okay, now I come to shearing stress. One by one we are discussing. First we discussed bending moment, shear force diagram, and bending moment diagram at a different loading condition of the different beam. Later we came to discussed about the bending stress and complex structure. Now we are recapping the information what you studied in the earlier semester. Shearing stress. Now in this case, right, where is the bending? Shearing stress. Now in the shear force diagram and bending moment diagram, when the bending moment is more, either the load is acting opposite direction, or where the shear force is maximum, or where the shear force is change in sign from negative to positive. Which case the bending moment is maximum. I already have given some clue. Which case? You already studied, no? Where is the bending moment? Where is the maximum bending moment? For maybe this is a simply supported beam. This is shear force diagram, right? SFD. Now this is the bending moment diagram here. But this is very important information when we are going to discuss the design of transmission element. Whatever the concept we are discussing, the same concept we are going to apply in the subject also the next semester. Now bending moment is maximum. Sorry. So when the shear force change in direction, I mean that place bending moment is maximum. I mean, we can say in the opposite direction when the shear force, when the bending moment is 0, during that time shear force is maximum. Sorry. Okay, see here, earlier case, whatever we discussed, that bending stress is 0 at the neutral axis, but in shearing force, in the shearing stress, the shearing stress is maximum at the center of the axis of the geometry. Now I am taking here rectangular shear force diagram, shear stress distribution. In this is the solid circle shear stress distribution. I mean, this is the circle, a hollow tube when subjected to shearing stress, how the shear stress behavior. Now if I put one more layer, how it will be the shearing stress here? How it will be the shearing stress? Okay, now I put here the shearing stress again going to be like this, like this. Okay, now this is the at a different cross section of the components, how the shearing stress is playing in how the shearing stress distribution we have to understand. Now I come to this. This is the I section of the shear stress distribution. Now we already discussed, right? In the bending stress. In the bending stress, it will be at the middle layer, neutral layer, 0, but here not 0. This kind of question you may expect in the any competitive exam. Now this is the composite built-in section. This is a multiple section connected. This is stress distribution like this. Now it's T section. If you understand this I section, T section is very easy. I mean, T section is nothing but like this. Okay, this is T section, half of this. Okay, now we discuss shearing stress and bending stress and deflection of the beams. Now I come to this thin cells. In thin cells, what are the stress components? Please, someone tell that. In thin cells, what are the stress components?
So longitudinal stress and hoop stress.
Hoop stress. And what is the basic principle we are using to design the thin cells? I mean, are you heard about the bursting force?
Yes, sir.
The bursting force, where it is coming? Bursting force is equal to resisting force, right? A resisting force is nothing but that body behavior. I mean, that outer cell behavior of the drum or cell or tank, circular tank. The bursting force, where it is coming? Bursting force. Why we are considering bursting force is equal to resisting force? What is the bursting force?
Sir, internal pressure applied by the fluid flowing.
Yeah, exactly. Thank you. I mean, bursting force is equal to resisting force. The bursting force is nothing but when you have a thin cylindrical cell or tank, closed tank, when you are filling different types of fluid, when you are filling water, it's in that pressure developed by water in the circumference, in the internal pressure developed by the water is different when you are comparing other fluid. For example, castor oil. I'm using water. Another one thing is castor oil. Okay, castor oil. Okay, now fuel. Whatever you are filling, the fluid behavior is, fluid property is different. Water density not high dense fluid as compared to castor oil. Castor oil is dense fluid, right? But when the castor oil filling inside the cell, that the different pressure is creating. So it depends upon the fluid properties, the cell pressure varying inside the pressure. That is called bursting pressure. Now, that the bursting pressure is equal to resisting force. But actual design condition, bursting pressure, what is the design condition we should consider? The resisting, can anyone tell me? Resisting force greater than the bursting pressure. While we are going to design the shell, we have to consider this. Okay. Now this is you are very well known. I mean, now just I recap here. I mean, circumferential stress or hoop stress, right? Now circumferential stress or hoop stress. Now this is the two ends now closed. Now this is the two ends of the shell is closed. Tank, cylindrical tank closed, right? But when you fill the water or any fluid, the circumferential force, circumference is created because this is due to contact on the water or any fluid contact on the circumferential direction. We are considering that. Then the cross section we are considering this. This is the cross section we are considering, while this is the cross section along the longitudinal direction. We are considering this. Okay. Now, when the circumferential stress or pressure acting inside the cylinder, now we are considering this portion. Okay, but the pressure is acting along the circumferential direction, but we are considering our dimension, our geometry of the cell, we are considering this direction. Okay, this is length L. I mean, here length L and the thickness is T. Length L and thickness is T, and two side 2 into L into T into sigma C. 2 into L into T into sigma C. That's what I'm considering here. Just T. Now PDL is nothing but the bursting force acting inside P into D into L. This is the projection area is D, length is L, P D L. How much force is acting now? Bursting force is P D L. Now we are finding the sigma C equal to PD by 2T. Now when we are considering the longitudinal stress, I mean at the end closed plate, the stress is acting with the pressure, fluid pressure is acting here. Okay, that fluid pressure. Now what is this dimension? This is a cross section, circular cross section. Then P into 5 by 4 D squared is equal to, then what is this resisting force developed by the material here? Thickness of the closed cap. Thickness of the closed cap, I'm considering T, right? Sorry. Thickness of the closed cap is the T. Now I'm considering this end. This thickness of the cap. Because now the longitudinal force is acting here. Longitudinal pressure. Okay, longitudinal force. Longitudinal stress. P with the effect with because of the fluid. Now P into pi by 4 D squared into pi dt. Now this circumference area pi d into thickness T. Now we are able to find out, see here pi dt into sigma L. Now we are able to find out sigma L, longitudinal stress, PD 540. Now why we are discussing this? If you know this inside the pressure, if you know this inside pressure and how much material yield stress value, then you can define your dimensions of the shell. I mean, means nothing but thickness of the shell. If you know this longitudinal stress, we able to predict define your thickness of the shell. And even I mean, in this case also we are able to find out the thickness of the shell. But if you know this hoop stress or circumferential stress, you are able to predict the length of the shell. PDL is equal to 2 into L into T into sigma C. Okay, I mean the length or thickness, whatever you can define if you know these parameters. The parameters should be within the yield distance. Okay. Now I come to furthermore. Now whatever we discussed, different stresses and different components. Now we come to the bearing pressure. What is bearing pressure? Bearing pressure is means it's also contact pressure, right? Now when the body is pressed against the another body, the compressive stress is generated, right, on the external surface. On the external surface is called a bearing pressure or crushing stresses. Now here bearing pressure, I mean, why we are saying bearing pressure? Suppose if I'm not using any fluid, a fluid in that sense, lubricant oil, then what we can say that is frictional force, right? Obviously. Now this is in side view. I'm trying to draw in the this is a front view of the journal and bearing. Now I try to draw in the front view. This is my journal. Sorry, this is my fixed bearing. This is, I mean, inside is my journal is here now. This is this portion, fixed bearing. Now my journal is here. When the journal rotates, what will happen? This is my journal. Now the journalist rotates, said that what will happen now? I mean, if we are not applying any pressure, any fluid, I mean any lubricant oil, any lubricants, what will happen? It's a frictional force going to be developed in between two surfaces. I mean, our main purpose is to avoid the frictional force in between two surfaces for smooth power transmission. Hence, we are applying the lubricant oil. Then, when you are applying the lubricant oil, when the journal is subjected to radial load, when the journal is subjected to radial load, I draw it here. When the journal is subject to radial load, what will happen? I mean, now this is the force acting this region only. The pressure, bearing pressure acting in this region, the maximum bearing pressure at this point of contact only. Because this cylindrical body, this cylindrical rod, if you take planar boundary, planar surface, if the planar surface occupy more space, but when you take cylindrical object, if you keep it any plane surface, it will be the mostly we can say that point contact, right? When you apply the bearing load, when you apply the external load on the journal, now we is filled with the lubricant oil. Then during that time, this point contact, now more in this point contact, more bearing pressure is acting. This is the bearing pressure profile when the journal is rotating with the help of when the journal is freely rotating with the help of the appropriate lubricant oil. I mean, we are applying the lubricant oil to avoid the frictional force between the two surfaces. Hence, smooth power transmission can be done. Okay. Now this is the, I mean, bearing pressure is equal to P by LD. I mean, we are going to discuss in this in the like static condition and dynamic condition. Okay. Now, I mean, this is the bearing pressure is nothing but P by LD. Now P by LD, this is number of reverse use. Okay, P by LD here, P by LD. Okay, now thermal stress now just we are just we are touching that. What is thermal stress? Thermal stress is nothing but L alpha delta T. It's nothing but, I mean, this thermal stress, sorry, this is L alpha T. Delta L is equal to L alpha T. Elongation due to elongation due to temperature. Okay, now thermal stress we are able to find out from alpha T. Okay, no problem. Now this is the self weight. I mean, impact stress. We most of the types of stress we already discussed. Now the last one is impact stress. Impact stress. In this case, this is the body. I mean, the component is now this is a collar. This is the dead weight. The dead weight where it is falling, at which height it from falling. Based on that, impact stress is going to play. Now, suppose the H is 0. This now what kind of stress now? Anyone tell that? Suppose H is 0. What kind of stress? Impact stress, I already gave you good example in the beginning, earlier class, in the first class. I mean, due to car crash analysis, most of the things they are considering impact stress, impact load. Now, suppose if I am considering H is negligible, H, at which case it will be H is negligible, what type of stress?
Sudden stress.
Yeah, static stress. Thank you, but thank you. Okay, then now come to the type of stress and type of loads. Come to the conclusion. Then we go for few problems based on time availabilities. This time now. Okay, I stop it here. Yeah, please only one slide. Okay, this slide. This is tensile load. This is the compressive load. This is the, I mean, shearing load. This is a bending moment. Going to be a bending stress. Okay, this is a twisting moment. Okay, going to be a torsional shearing stress. This is a combined effect. Combined effect. I mean, the combined means a torsion and bending combined. Is now. This is another way. With this lever assembly. In the lever assembly, sorry, in the liver assembly, what are the stresses acting? See here. Now, I mean, this is the river is connected in the hollow tube. The hollow tube now here, I mean, normal stress is 0, but the liver is connected here. The vertical load is acting in y direction. Hence, shear stress is going to be there because this is offsetted from the our tube. The force is offsetted from the our tube. Obviously, shear stress will be there. Okay, now due to this offsetted forces, the turning moment will be there when this is a bending moment with respect in the z direction, but y direction bending moment 0. But with respect to z direction, bending moment will be there, and this is also twisting moment with respect to the distance between the center of the axis of the tube and the force acting distance. Then the offset, based on this offset distance, we can define the twisting moment. Okay, this is the things for simple understanding. Now, then the next class we are going to discuss the problem, and we are going to enter the more detailed information about the design components of the design with respect to the static loads and the different stresses. Whatever we discuss, those information will be useful while we are going to discuss the problems. Yeah, thank you guys. If you have any doubt, please, I'm ready to clarify your doubt. Please go ahead. Yes, slide I will share you the next class. And I mean, I do one thing. Whatever I prepared, I share the slides in the tomorrow class. Okay. And the end of this chapter, I will share the updated slide. Okay. Is it okay? Yeah, thank you, Sakil. I see any questions are there in the chat box. No questions. Yeah, please, if you have any questions, please go ahead. And Sia, Kalyan, are you there in the meeting?
Yes, sir. Yes, sir.
In between class, how many students were there in the meeting?
Almost 58.
60?
Oh, yes, sir. 60 student.
Okay, okay. Okay, guys. Thank you very much. If shall I close the meeting, Sia?